Welcome, everyone. So, have you ever actually stopped to think about the invisible architecture of our digital lives? Every single time you scroll, search, or stream, there's this massive, incredibly complex engine just humming along in the background. Today, in this explainer, we're going to completely demystify the algorithms that govern our digital world. We're going to look straight at the mathematical blueprints to understand exactly how machine learning models think, learn, and connect the dots.
It's a question we've literally all asked ourselves at some point, right? How exactly does Netflix recommend that perfect, totally obscure movie? Or how does Google seemingly read your mind and instantly pull up the exact web page you were looking for out of billions? It can feel like magic, or maybe even a little bit of digital telepathy. But the truth is actually much more structured, and honestly, a whole lot more fascinating.
Because the secret ingredient isn't magic at all. It's math. Okay, let's dive into this. It really all comes down to linear algebra. We are going to unpack these specific, super elegant mathematical structures that allow computers to process massive amounts of information. By the end of this explainer, you're going to see exactly how basic rows and columns of numbers translate into the incredibly smart systems we rely on every single day.
So, here's our roadmap for today. We'll start with the math behind algorithms, move into the linear algebra of similarity, then we'll navigate graphs and PageRank. After that, we'll look at optimizing with computational graphs, and finally, we'll tie the whole shebang together.
All right, part 1, the math behind algorithms. We'll be using Charu C. Agarwal's textbook, specifically jumping into chapters 9 through 11, pages 435 to 570, to take a direct peek under the hood of the AI engine. Moving right along to part 2, the linear algebra of similarity, or as I like to call it, the ultimate matchmaker.
Think of algorithms as the world's most aggressively data-driven matchmakers. Before a system can recommend anything to you, it first has to understand how two things actually relate to one another, and it does this using a similarity matrix. But they need strict rules. Enter positive semi-definite matrices. I know, it sounds like a total mouthful, but in plain English, this just means our similarity matrix is mathematically sound. It's symmetric, meaning the similarity between item A and item B is exactly the same as B and A. And crucially, having non-negative eigenvalues ensures our similarity measurements are actually robust. If a matrix isn't positive semi-definite, well, the algorithm's geometry just breaks down, and its matchmaking goes completely out the window.
And this brilliantly illustrates what happens next. When you have mashed together data points that you just can't separate with a straight line, we apply a kernel method. This relies heavily on those positive semi-definite matrices we just talked about to mathematically project that data into a higher dimension. It acts literally like a pair of 3D glasses for the algorithm. Suddenly, boom, the hidden patterns become completely obvious, the data becomes linearly separable, and the algorithm can easily distinguish between the two groups. It's so cool.
Okay, part 3, navigating graphs and PageRank. This is where we get into mapping connections. So now we're shifting gears. We're moving from comparing isolated data points to mapping out vast interconnected worlds, like the internet. To navigate these insanely complex webs, algorithms turn relationships into mathematical graphs. Just imagine a web server clicking links completely at random between 4 web pages in an aperiodic and strongly connected Markov chain. The arrows are the links, and the numbers, those are the exact probabilities of clicking that specific link. Like if you're on page F, you got a 60% chance of jumping to C and a 40% chance of jumping to B. It perfectly models how movement naturally happens within a network.
But here's the thing. Computers don't look at arrows and circles, right? They look at tables of numbers. Those transition probabilities we just saw get organized into a highly structured stochastic transition matrix. Notice how in row F, we have that exact same 0.6 probability for column C and 0.4 for column B. This matrix right here is the precise mathematical language the algorithm uses to understand the layout of the entire network.
Now this is where the magic really happens. How does Google actually know which page is the most important? I always kind of joke that eigenvectors sound like a comic book villain, but they are absolutely the quiet heroes of the internet. By analyzing that transition matrix, the algorithm computes the left eigenvectors. This calculation reveals the steady-state probability, which is basically just where our random web surfer is most likely to end up over time. The higher the probability, the higher the prestige. And guys, this is the exact math behind the ultimate high school popularity contest, PageRank.
Moving right into part 4, optimizing with computational graphs. Let's look at how algorithms actually learn.
So, we've compared data, and we've mapped relationships. But how does an algorithm actually learn from its mistakes? Well, think of a neural network as a highly efficient mathematical assembly line.
Raw data enters on the left side through input nodes, and as this data travels forward along the paths toward the output node, it gets multiplied by weights, labeled as W1 through W5. These weights are essentially the machine's current best guess at just how important each piece of input data actually is. This forward movement is exactly how the neural network makes its initial prediction.
But of course, that initial prediction is almost never perfect right out of the gate. So the machine has to learn, and it does this in 3 distinct steps. Step 1 is the forward pass we just talked about, where it makes the prediction. Step 2 is to compute the loss, which is basically just a mathematical way of measuring exactly how wrong that prediction was. And step 3 is the absolute most critical one, the backward pass. Using a calculus principle called the chain rule, the algorithm sends that error signal backward through the graph. It calculates the derivatives at each node, which allows it to tweak the weights and fix the machinery for the next time around. This whole process, that's backpropagation.
To actually see this practically in a logistic regression model, check out the objective function. This equation mathematically aggregates the loss, or the error, over a single training instance. Through something called stochastic gradient descent, the algorithm continuously evaluates this function. It's constantly turning the dials of its weights, step by step, instance by instance, until that error is as absolutely small as it can possibly be. It's basically this relentless, mathematical pursuit of accuracy.
So the crucial point is, we've reached part 5, tying it all together, the unified picture. We've covered a lot of ground in a really short time today. We've moved from similarity matrices through the Markov chains of graphs right into the gradients of computational learning. To completely summarize our narrative arc here, algorithms absolutely do not have human intuition. Instead, they first compare raw data using the matchmaking of similarity matrices. Then, they navigate complex relationships and figure out importance using graph matrices and eigenvectors. And finally, they use the automated assembly line of computational graphs to calculate errors and literally learn from the data. Every single one of these miraculous capabilities is completely powered by the beautiful underlying structures of linear algebra. Which leaves us with a final thought to ponder. We've seen how these algorithms mathematically map out importance, similarity, and learning to predict human behavior. So if linear algebra is powerful enough to map the entirety of the web and mimic the learning process to shape what you see, read, and buy, what invisible graphs are shaping your decisions today? Thanks for joining me on this explainer. Keep learning and keep looking for the math behind the magic.